Hey everyone. Today I thought I'd start by showing you a favorite quote of mine. I love to collect quotes, so if you ever come across one that you love, please share it with me. So I'll let you take a second and read that. And then go ahead and start on your notes page. Today we're going to be able to use the distributive property to evaluate and simplify expressions. And I know you've learned about the distributive property before, so hopefully much of this will be a review. But I want to talk about the difference between evaluating something and simplifying something, because sometimes those simple directions can trip us up. So evaluating is when we actually find the value of an expression. So if I said evaluate 5 plus 10, we would get 15. That gives us an actual number answer. We have the value. Whereas simplifying is when we find an equivalent expression with no like terms or parentheses. So we're replacing something with an equivalent expression that is fully simplified, meaning that there's no more like terms that can be combined. There's no parentheses that we need to do anything inside of. It's fully simplified. And here's an example. If we had 3x plus 2x plus 4, here's like terms that can be combined, and so that's not simplified. So when we combine them, we get 5x plus 4, and this is fully simplified because I can't combine 5x and 4. They're unlike terms. This is a variable term, this is a constant term. So we're done at that point if the directions said to simplify. All right, so let's refresh our brains about what the distributive property is. Actually, let me go back and only do one at a time. So if we have a number or a variable being multiplied by a sum or difference in parentheses, and that's a big key component there. What's in parentheses has to be a sum or a difference. That's when we can use the distributive property. And we simply take the outside number and multiply it by each of the inside terms. And you probably have learned in the past to use the little arrows to remind us visually that we need to multiply by each of the terms and we don't leave anything out. So this one would result in AB plus AC. Don't get confused if A happens to be on the back side of the parentheses instead of the front side. We still do the same thing. We still are multiplying A and B. We're still multiplying A and C. It really doesn't matter. And then we have the same thing if it's a difference. So if we're subtracting, we still multiply A and B, we still multiply A and C, it's just that now it's a subtraction in the middle. And same thing if the A is on the back end. All right, so hopefully that looks familiar to you. Let's take a look at a few examples. If we have 6 times the sum of 8 and 10, we could, in theory, using the order of operations, just do 8 plus 10 would give us 18 and multiply it by 6. But that would be a little harder to do mentally without pulling out a calculator. This allows us to do it a little bit more mentally because we can do 6 times 8 and then we can do 6 times 10, just like I have written here. And then that's pretty simple from there. 6 times 8 is 48, 6 times 10 is 60. Add those together, we get 108. Pretty quick and easy. Here's one that's a little bit more complicated, okay? And my arrows got a little out of control over here. There we go. So we're going to distribute this -2 to each of those inside terms. And so I rewrote it just like this. -2 times each of the inside terms. You can pause if I'm going too fast so you can get caught up. And then I'm going to multiply that. So -2 times 3x squared gives us -6x squared. -2 times 5x is -10x. -2 times 1 is -2. And then I can simplify it farther because I don't need these parentheses in here. So if I'm adding a negative, that's the same as subtraction. So this is the same thing. Okay. Now, let's look at some more mental math type examples. If we have 7 times 49, honestly, that would be annoying to me to have to do mentally just as is. But I could replace 49 with another expression, such as 50 minus 1. So look what happens when I replace it with 50 minus 1. 7 times 50 is 350. 7 times negative 1 is negative 7. So 350 minus 7 is 343. I can do that pretty easily on paper or mentally by using the distributive property. Here's another one. 5 times 210. I can replace 210 with 200 plus 10. And then using my distributive property, 5 times 200 is 1,000. 5 times 10 is 50. So I get 1,050. And that makes it pretty easy to do mentally. On the back side of our paper here, we've got some vocabulary, such as term. This is a number, a variable, or a product or quotient of numbers and variables. And here's examples. Here's a plain old number called a constant term. Here's a plain old variable. Here's a product of a number and a variable. Here's another product. Here's an example of a quotient. So a lot of things are called terms. Like terms are terms that contain the same variables, and if they have the same variables, they have the same powers. So for instance, 3x and 5x, same variable to the first power. 2x squared and 6x squared, same variable to the second power. A non-example would be 2x squared and, 4x cubed. Those are not like terms because x squared and x cubed have different powers. Those are not like terms. And then a coefficient is, I think we've talked about this before, but a coefficient is the numerical factor of a term. Oops, there's a typo. So for instance, in 2x, 2 is the coefficient. In just x, 1 is the coefficient. Okay? So if a variable is by itself, it has a coefficient of 1. So here we're going to look at simplifying an expression using the distributive property. And I didn't write it, I left it all typed out for you. So we're going to use our distributive property, and you can draw the arrows if you want. So 4 times a squared gives us that. 4 times 3ab gives us 12ab, and then minus the 1ab. Notice that they wrote multiplicative identity in here. This is probably not a step most of us would take, but they are justifying how this is 1ab. That when we have that variable term with no coefficient in front of it, it's the same as 1ab. And we use the multiplicative identity to justify that. But most of us would probably never bother to actually stop and justify it that way. If you want to write the 1 in, fine, go ahead. But it is not something I'll be looking for. So then 4a squared plus 12ab minus 1ab. Again, here's a step where I don't know that I would take the time to justify, but they kind of did reverse distributive property here and said that it's 12 minus 1, and that difference would be multiplied by AB. But I think most of us would probably just say, okay, well, if I have 12 of these and I subtract 1 of these, that means I have 11 of these. So it just simplifies to 4a squared plus 11ab. All right, so what I want you to do is I want you to pause right now and try those examples at the bottom of the page, and then come back and check your answers. So hopefully you've done all of these. Here's our answers. Okay, again, in number 1, I don't know that I would normally separate this out, but it does justify why it works. But if you have 12 A's and you subtract 1A, you get 11A. Over here, same thing. I probably would just go 3x squared plus 10x squared is 13x squared. And I'd probably skip this step. I showed it to you, but I'm not going to be looking for that. Number 8, you could simplify here first, like I did here, or you could use the distributive property. And there you go. You can check the rest of those. And we will do a little bit more work with the distributive property tomorrow. And have a great night.